let's review our redox stuff. It's been a while. You haven't had it since 107, so you may have forgotten what's going on there. This is from 17.1 in the book. All right, so what are our objectives? We'll describe defining traits of redox chemistry. We will assign oxidation states to elements and use that to determine which element is oxidized and which element is reduced. We'll identify the oxidizing agent and the reducing agent. And finally, we will balance redox equations using the half reaction method. And I will tell you right now, I summarize a bunch of their steps. If you find their steps easier, do it that way. Conceptualize it that way. I find it easier to think of it my way. So that's what I'm going to present to you. All right, so first things first, what is a redox reaction? The oxidation state of one or more of the elements changes when you go from reactants to products. Okay, so in this particular case, iron is being reduced and carbon is being oxidized. If the thing is reduced, it is the oxidizing agent, and if the thing is oxidized, it is the reducing agent, which is not at all confusing, I'm sure. There are two main mnemonics that people use to memorize what's going on here: oil rig and Leo goes grr. Use whichever one works best for you. So oil rig, oxidation is loss of electrons, reduction is gain of electrons. Leo goes grr, loss of electrons is oxidation, gain of electrons is reduction. And I don't care which one you use so long as you use the thing that works for you. All right, so how do we balance these things? We have what's called the half reaction technique. You write one equation for the oxidation half of the reaction and a separate equation for the reduction half reaction. Then you balance the number of particles in each half reaction. So I call this conserving mass. Third step, you balance the charge in each half reaction by adding electrons to the appropriate side. I call this conserving charge or energy. Step 4, you multiply each half reaction by the appropriate whole number to make the number of electrons in oxidation equal to the number of electrons in the reduction equation. Again, I call this conserving energy, but it's for the overall. And 5, you add the two half reactions together to generate the equation representing the redox reaction. I have summarized this into a list of 5 things: pull half reaction, balance mass, balance charge, balance overall charge, and recombine. And the reason that I did that is that this fits in a smaller place on the slide than this whole thing. So hopefully you're following that. Let's try to apply it. All right, so we have copper chloride plus aluminum becomes aluminum chloride and copper solid. Now I can write this as an ionic equation, which I've done in the middle there, and then I can write it as a net ionic equation. We're going to start from that net ionic equation when we try to balance this. Why? Because otherwise you're looking at a whole lot of stuff, some of which is completely extraneous to what we're doing here. All right, so how do we pick out the oxidizing agent and how do we pick out the reducing agent? Well, copper here goes from 2+ on the reactant side to 0 on the product side for following our oxidation number rules. So if we are going from 2 down to 0, that is, you are gaining electrons, it is reduction. We're going to pull that one first as our half reaction. Now it says to balance for mass. We have 1 copper on both sides. We are balanced for mass, but we are not balanced for charge. We have a 2+ on the left and we have a 0 on the right. So we're going to add electrons in order to get both sides at the same charge. In this case, we need 2 electrons to the side with the copper 2+. So now we have balanced for mass, we have balanced for charge. We're going to go ahead and do the other half reaction. So we pull the aluminum half reaction. We're going from aluminum solid to aluminum 3+. We are already balanced for mass, so we go back and we balance for charge. And in this case, we add 3 electrons to the aluminum 3+ side and we get 0 charge for both sides. We have done steps 1, 2, and 3 for both things. Now, when you do steps 1, 2, and 3, you've balanced both half reactions. In one of your half reactions, you should add electrons to the reactant side, and in one of them, you should add electrons to the product side. And if you don't, you have done something wrong, because you don't have an oxidation and a reduction, you have an oxidation and an oxidation, or a reduction and a reduction. And that is not a thing. That's not okay. So we have to be transferring electrons. That's what redox is. One of your half reactions has to be oxidation. One of your half reactions has to be reduction, or you have done it wrong. So that is one of your gut checks. Now we're going to do steps 4 and 5. We must now balance for overall charge. We start with both half reactions and look at the number of electrons on the left and the right. We must get these to be equal, and we want to use the smallest numbers we can to do so. Find the least common multiple. It may have been a while, but that is the smallest number that you can get that is a multiple, meaning you multiply your number times 2, 3, etc. In this case, our numbers are 2 and 3. They're both prime numbers. So when they're both prime numbers, we just cross multiply. So the entire copper reaction gets multiplied by 3. The entire aluminum reaction is multiplied by 2. That gives us 6 electrons on both sides of the reaction, so the electrons will cancel out. So we add these equations together, reactant side to reactant side, product side to product side, and there we go. We have our balanced redox reaction. Now, if they were not both prime numbers, then we could divide by common primes. Like say it was 4 and 8, common number that would go together would be 2. You would divide both by 2, and then you would divide both by 2 again, and then you would multiply them by each other. Alternatively, you can list out their multiples and then circle the one that's the first you come to that's the same on both. Whichever works best for your math brain, you should do that method. Let's go on to do a more complicated example where you need to use water and acid or base to solve for the problem. Alright, so this time we have an ionic equation at the start. We have nitrate and copper going to nitrogen oxide and copper 2+. These ions could come from multiple sources, but we got rid of the spectators that don't do anything in the reaction. This can be confusing in lab. Remind yourself, you get rid of the spectators to simplify the reaction, and if you're not sure if the reagents are related to your balanced chemical reaction, write the dissociation equation for each of the aqueous reactants. It should become obvious where you get your ions from. I digress. So when we are balancing our half reaction, or balancing redox equations, we first need to break the half reaction. We have, in this case, 2 species with nitrogen and 2 with copper. We don't even need to know oxidation number. We can just split the half reactions by the cation. So I'm going to split the nitrate and nitrogen dioxide first. Now we balance for mass. In this case, we have 3 oxygen atoms on the reactant side, right there, and 1 on the product side. So we need 2 more oxygen atoms on the product side. But where are they going to come from? This is an aqueous solution. It's in water, so we can get it from water. Now we're going to assume that the solution is acidic because it doesn't say, and I just make that assumption because it's easy. That's how we're going to get our hydrogen to balance out the hydrogens from the water. So here we put on our 2 water molecules, and then once we put on 2 water molecules, we have 4 hydrogens that we need to account for, so we put 4 hydrogens on the other side. And now we need to balance for charge. So we have 4 times 1 plus a -1, right? Because we've got 4 H pluses and 1 NO3 minus on that side. And together, that makes a charge of 3. we have no charge on the other side whatsoever. Nothing going on there. So we're going to go ahead and add 3 electrons to the reactant side. That balances us out. At this point, we're going to go ahead and deal with the copper. So our copper is going from 0 to 2 plus. We don't have to worry about balancing mass because it's copper on both sides, just one of them. But we do need to balance charge. So we're going to need 2 electrons to make that work. At this point, we're going to go to steps 4 and 5 because we've done steps 1 through 3 for both of our half reactions. So we're going to balance for overall charge. We start with both our half reactions, look at the number of electrons on the left and the right. And since we need to get these to be equal, we realize that we need the smallest numbers in order to do that so that we don't have to go back and cancel things out. In this equation, 2 and 3 are both prime numbers. We can just cross multiply. Make sure that we distribute the 2 and 3 all the way across our equation. And then we're going to add reactant side to reactant side, product side to product side. So overall, our balanced chemical equation becomes 8 H pluses plus 2 nitrates plus 3 copper solid plus 2 nitrogen oxide plus 2 water, and then 3 copper 2 plus. But what if we were doing this in a basic solution instead of an acidic solution? Clearly this would balance slightly differently, so we're going to do that next. Alright, so if the solution is basic instead of acidic, we can solve the problem for the acidic case and do a switcheroo at the end. So we start from the same place as last time. Copper balances the same way. When we break out the nitrate half reaction, we have oxygen. So we go ahead and we do it for H+, just like we did before, but here at the end, we are going to add hydroxide to both sides. What do you make when you add H+ and OH-? We make water, our good old friend. So we're going to go ahead and add those things together. H+ and OH- making water. And we end up adding 4 hydroxides to the product side. We now have water on both sides of our equation, so we're going to cancel out the excess water. We simplify it to 2 water on the reactant side plus nitrate going to nitrogen oxide and 4 hydroxide ions. At this point, we balance for charge. On the left-hand side, we have a -1 charge from the nitrate, and on the right-hand side, we have 4 times -1, -4 from the hydroxide. Since both sides have to have the same charge, we're going to add 3 electrons to the reactant side, which is the same side and the same number of electrons that we added before. If it were not, we would have done this problem incorrectly. When you switch it over to a base, you should still be adding electrons to the same side you did before, or you messed it up. Let's go on to balance our overall charge and recombine our equation. So in this case, again, we still have the 3 and the 2, right? We do our cross multiplication, and we distribute all the way through, and then we simplify. So now we have the solution with hydroxide instead of hydrogen. Not too bad, not much different. We could have also done the H+ to OH- at this step. It actually doesn't matter. Do whatever makes sense to you. So, to summarize, a redox reaction transfers electrons between chemical species. The oxidation number of 2 atoms will change from one side to the other. Reduction is the gain of electrons. Oxidation number goes down. Oxidation is the loss of electrons, and the oxidation number goes up. The oxidizing agent is reduced, and the reducing agent is oxidized. And if you're going to use the half reaction method, you can follow these 5 general instructions. Pool the half reaction, balance for mass, balance for charge, balance for overall charge, and then recombine your equations.